Hello, my name is Ajda. I'm a young researcher at Laboratory of Microelectronics, and today I will present a fully differential charge amplifier for vapor trace detection system. First, I will start the presentation with motivation. Then I will describe the differential capacitive sensing for one channel of artificial noise system, following the presentation of chopping amplifier and the reason why ripple reduction loop was added in our system. Some simulation results will be presented, and I will conclude the presentation with some plans for future work. We want to detect extremely small capacitive changes. When talking about extremely small, we have in mind the zeptofarads. In other words, we want a system that will have a very big signal-to-noise ratio. The chip for 265 channel artificial noise will be made in CMOS technology. The disadvantages of these technologies are that operational amplifiers have relatively big flicker noise and offset voltage. Well-known methods to get rid of these non-idealities are auto-zeroing, correlated double sampling, and chopper technique. We chose chopping because it has the best properties of thermal noise. And now let's first look at how one channel of artificial noise is built up. It is composed from two input DC voltages. Then these voltages are chopped using the input differential chopper that generates square wave signals. These two voltages, V in1 and V in2, are connected to sensor, and then it follows voltage to voltage amplifier, and in feedback loop we have another chopper and feedback capacitors. The novelty of the proposed system are also sensors. One sensor is composed from two differential sensor pairs, and in this way we get differential signals through node ENN and ENP. The basic concept is these differential sensor pairs are excited with square wave signals that are shifted by 180 degrees. Chopping is used when applying low frequency and small amplitude signals, as in our measuring case, where absorption and desorption of target molecules is relatively slow. So let's now look at the basic concept of chopper amplifier. Here in this picture, we can see the simplified block diagram. At frequency domain, we see here the signal spectral in the baseband. This signal gets modulated up to harmonics of square wave signal, and this signal is then amplified, and then it hits the demodulator here. And at point C, all the energy of this signal is back converted to the base band. Okay, I will go here. Here, where noise and offset of the amplifier presented with dotted line. It's modulated up just once, right before the low pass filter. And if we strategically design low pass filter, all the energy from modulated offset and noise is filtered out. But in the end, in the ideal case, we are left with signal spectral and some residual noise. And here, on the right picture, we can see our proposed fully differential charge amplifier, which also contains choppers. At the output of the charge amplifier, we get an amplified DC signal and some ripple. This ripple here is due to offset and flicker noise of transconductance amplifier GM1. To get rid of this ripple, we can apply a low-pass filter, as in simplified block diagram, but we don't want to integrate another low-pass filter due to air and power consumption. So we rather implement a ripple reduction loop, which is presented here in the schematic. So this is ripple reduction loop added in our charge amplifier. So the main purpose of this ripple is to create the same amount of current as the ripple is sensed at the output of the charge amplifier. And this ripple is then added or subtracted from IP and IN. And if everything is designed correctly with added ripple reduction loop, there should be no ripple at the output of charge amplifier in steady state. So the proposed topology was simulated in Cadence in 180 nanometer technology. We first did the simulation where ripple reduction loop was switched off. We set the offset voltage of transconductance amplifier to 5 millivolts, which is a typical offset of CMOS amplifiers, and calculated and simulated output voltage ripple is equal and is in both cases equal and is 25 millivolts. And in the right picture, we see the results of simulation when ripple reduction loop was on. And it is clear that ripple reduction loop effectively suppress the ripple. So to conclude, theoretically, it is possible to reach a sensitivity of 3 zeptofarad per square hertz, but this yet has to be proven with simulation. Thermal noise in baseband increases by 7% due to folding. However, we are planning to continue our work toward more efficient topology, possibility to design and implement an array of such amplifiers, and also we are planning to optimize the power consumption. Thank you for your attention. Any questions?
Thank you for the presentation. Any questions? Who goes first? Yep.
Thank you for the presentations. I was wondering why do you avoid introducing the filter inside the design and replacing it with that? Can you explain this more?
Here, this filter.
Yeah, no. Sorry, the low-pass filter that you try to avoid. Why do you avoid it? What are the reasons behind it?
Because due to power and air consumption, due to bandwidth loss, and so we rather implement ripple reduction loop.
Okay.
Because also we cannot make the low-pass filter because it's high-order low-pass filter, and it takes a lot of air on chip. And it's not good.
Okay. Thank you.
Anybody else? If not, then thanks again, Ajda, for your presentation.